Yesterday we talked about a multiple access channel, which models the uplink of a wireless communication system. So I mean, the idea is if you have a base station and mobile stations, that actually, I mean, there's many other examples of this too, right? I mean, if you have the central office of a of the telephone system, the copper distribution, you also have, you know, modems in homes, right? And so you have these twisted pairs which go to the homes. Right, and usually these are bundled together. These twisted pairs are, for at least for some part of their distance, tightly bundled. And then if we think of the, well, there's always two directions, right? Broadcast channel is the downlink. Broadcast channel is the downlink. So if you think of telephone line modems, it's the same idea. So with DSL, we also have broadcast channels and multiple access channels the other way, right? So this is wireless. So in fact, I mean, for both, these kinds of models are interesting not only for wireless communication, that's usually just the first thing we think of, I think, but they're just as interesting and useful for these problems. It just turns out that for these problems, the interference, even though the cables are packed very tightly, usually the interference, the crosstalk, is very low. But because the noise at the receivers is even lower than the crosstalk, you still need to get rid of the crosstalk. So you still need to do some kind of processing, both downlink and uplink. Just because the crosstalk is very low, simple algorithms are almost optimal for this problem. Here, crosstalk can be much stronger. So usually for wireless problems, we're often interested in more sophisticated algorithms, although nowadays the algorithms that are used here are basically the same as the algorithms that are used here. It's basically linear precoding or linear equalization for everything, right? I mean, it's everyone uses that. So the MAC is just the so-called uplink. So in both this type of network, that direction is uplink, that direction is downlink, downlink, downlink. I mean, wireless has many applications, right? There's cellular, like 4G, LTE. There's also wireless LAN, and of course, you know, the next 5G is supposed to probably unify everything, or I guess that's the vision of some people, perhaps. I don't know if that's what will happen, but we'll see. Let's talk, so we talked about an abstract model for the multiple access channel. So we like these memoryless models, as Shannon taught us, and channel models that seem to be extremely useful, at least for channel coding. They're very useful, probably a little bit more useful than for source coding, although that's not completely true either, I suppose. So the main problem is we have this issue that there are two messages, W1 and W2. That's the basic problem that we want to transmit reliably to the receiver, right? So, of course, you know, the modeling is important. So everything I've described here is for memoryless models. As we discussed a little bit yesterday, there are many channels, of course, with memory. Of which I would say there's two kinds, basically. One is, if you like, sort of stationary, ergodic, high-powered word, or a word that can mean many things. Just that time averages or statistical averages. So usually what we do here is we try to convert the channel with memory to one without memory, very often. The usual way of doing that is doing a Fourier transform, right? For linear channels, you just take a Fourier transform, then you convert a channel with memory, with inter-symbol interference, to one without, except that you get many parallel channels with different qualities. But the nice thing is you've separated the interference, you've taken it apart. And I mean, it's the same idea as for picture processing and video coding. I mean, everyone uses transform coding because it's the easy way of getting rid of memory, at least from second order statistic perspective. So that's the common approach, is transform coding. The other one is those that are what I would call non-stationary in a way, like block fading models. You know, like these are kind of funny models because you have memory over a period of time, and then you start another block and you have a new random variable, you stay constant, then you go another. So it's effectively a channel that changes in chunks. Very common because we're using OFDM in the first place, so we send in chunks and do that. So for these, often you have to think a little bit more carefully. So this is where outage, capacity or outage rates were very popular. I mentioned in the last, about 10 years ago, that topic received enormous number of papers. I think most papers by a pretty large margin in the wireless area were more on block fading, were on outage rates, outage capacities, than on ergodic. But I like to emphasize, again, I'll just repeat that, to me an outage problem is an intermediate to studying the full problem, which involves outage plus feedback. And when you combine outage plus feedback, you're back at ergodic again. Like the capacities you will get are exactly the ergodic capacities by coding over multiple blocks, because that's the best you can do, because feedback effectively lets you code over multiple blocks in a simple way. Right, so the feedback is very useful because it simplifies the encoding. So both are interesting to study, but the ergodic case, like the fully reliable case, is usually the one we're most interested in for message communication. If it's for video coding, of course, then we're interested in something else. Then we should add here a source model, something like, I don't know, let's call it U1N, and then you do a data compression. And then we should here add, like this will be a separation-based coding method, but that's the most common way we do these things. And then we have the reconstruction, right? Right? Then you would be talking about a distortion between here and here. And then also with block fading, you'll probably design the system differently for outage with feedback. And of course, the alternative approach is that you don't separate source and channel coding, because we know that source and channel coding aren't necessarily optimal, although if the two sources, which they usually are statistically independent, so we could talk about this problem, then doing separation-based encoding will be optimal again anyway. So if these two video sequences are statistically independent, which they will be, right? I mean, come on, unless they happen to be downloading the same video at exactly the same synchronized time, I mean, it doesn't, but anything else won't be correlated. So if they're independent, which is I think is a more common situation, then using this architecture will be optimal again, like separation-based coding. And then if you're talking about a block fading model, well, now how quickly you feed back and how often you feed back will be a function of a lot of things. Usually you're interested here in varying levels of distortion, right? Like if the data rate is bad, you might say, okay, I'm happy with a video that's coarser, or maybe there's usually some sort of threshold function where this guy is measuring how well the quality, usually it's downlink, right? But let's just suppose it was uplink for video communications, usually that way, not that way, but suppose it was that way if you're uploading something, but it doesn't make so much sense, but anyway. So we'll think about it from that perspective. The feedback you send, usually there's some threshold where you switch to a higher quality video once you see, oh, the rate has been getting better, let's switch the quality of the video. You sometimes see that happening, right? You're watching your YouTube video and suddenly it gets better. And the control mechanisms in the network that control these things hopefully have been getting better over the years. And, yeah. Okay, that's just a quick motivation. So we're really interested in studying the information theory for the ergodic case. One reason is because we get nice answers, right? So the memberless Shannon's theory is very compact, very nice, very general. So what we found is that the capacity region for this problem was given by the set of rate pairs satisfying 3 inequalities. Oops, I should have a union still. talk about the union in a moment, of I x1 y given x2 u, where u will be an auxiliary variable, but here it's very easy to understand what the role of this auxiliary variable is. It's just time sharing. And you can see it's time sharing because it's always in the conditioning. So whenever you see a rate sort of expression, and you see the u appears always in the conditioning, that means it's just an average. So it's just a time-sharing variable. And then we can still optimize which modes we're operating in, and px2 given u, right? And so we still have to optimize the conditionally, though we can still optimize this conditioned on what time we're operating in. Or alternatively, there's this convex hull representation which gets rid of the time sharing in a way other than only in the rate expression, where we have the set of R1, R2 satisfying the same expressions just without that u. And usually in most textbooks you will see this expression just because most people don't bother with the making the time-sharing random variable explicit, but the price you pay is of course that you have to add that convex hull operation. Now usually that doesn't bother people, but I think, to me, I like the more explicit expression more because it's more explicit. Like here like the time sharing is a little bit hidden. And plus, like I mentioned yesterday, it can be misleading because for some problems doing convex hull rather than time sharing is worse. So this is always the better approach in general. I mean, sometimes you can write it like this, sometimes you can't. So it's more safer to do it that way. Okay, so we talked a lot about the Gaussian channel, right? Additive white Gaussian noise channel, for which the region turns out to be simple. We don't need time sharing at all. It's just this pentagon. So this is rate 1, rate 2. This here is 1/2 log of 1 plus p1 by n. Or if we're using a complex channel, which usually we're interested in passband communications, you get rid of the half, right? But anyway, we'll keep the half. We just discussed real channels, so that would be baseband, but most channels are passband. So this picture is really per real dimension, the rates. And this is the mutual information. Right, so that's what it looks like, and we spent a lot of time talking about the corner points. These are interesting because to get to these rates we basically use a successive interference canceller. Decoder, then we talked about, okay, we can get that point to this point. And then in between, which is all the rates we're interested in, we had many techniques. We had time sharing or frequency sharing. You could use 2, of course, or TDM, FDM. Well, I don't want to call it that. Frequency sharing. We had, what else did we have? We had soft, so turbo processing, let me call it that, on the factor graph or the Bayesian network. We talked about rate splitting. And finally, we talked about this offset encoding, or delay-based coding method to move in between, right? We also looked at TDM, FDM, and we discovered that it touches one of these points. If we use TDM, FDM with power adjustment. I emphasize that because all these points do require you sometimes to send more power than other times, and this made us a little bit skeptical how good, what the importance is of these more sophisticated methods. But then we described a case, and you can find those in this example in the course notes, where if the signal-to-noise ratio is very low for one receiver and very high for another, so receiver 1 is much closer to the base station than receiver 2, and those gaps can be huge, right? I mean, can be 20 dB or more, and then the capacity region might look like this. And then I said that if you use FDM, you're about halfway down here. You're touching here, but you lose this potential here, right? Just to mention that it still is interesting to use successive interference cancellation, because for the weak user here, you're doubling the rates. Like, it doesn't look like you're getting much of a rate gain, but the weaker user gets twice the rate. That's the importance of that. Okay, so we studied a lot of other things. We studied the vector channel as well. I won't get into that. The concepts are similar, right, for a vector channel. Here we just have always the mutual information between x1y, x2u. We can always use successive interference cancellation, and that's the usual way of thinking about the problem because it simplifies things, you know, it makes things clear, right? That's why we focus on these corner points, is it's relatively easy to understand what one is doing there. And so we talked about vector, Mac, and we talked about duality. In particular, the one that interested us most is that if we have a broadcast channel capacity region, then it turns out there's a dual class of multiple access channels, and the dual class is you just take the certain matrices and transpose them and then add a sum power constraint on both powers. And then if you take the union over all capacity regions of those max, you can trace out the entire capacity region of the broadcast channel. And the importance of that is that this generalizes to vector cases. And the reason that's interesting, so for the vector case, so this is the scalar case. For the vector case, the capacity regions look like this, and then there's a flat piece, and then there's a curvy piece, R1, R2. This is for the BC. And it turns out that this insight of duality generalizes to this problem too. So in fact, what happens is you get max, if you optimize over the sum power, under the sum power constraints, the capacities of all the max, then you will also trace out the capacity region. And the interesting part about that is that the optimization problem of the covariance matrices that you're interested in for the broadcast channel is those are non-convex problems. But optimizing, finding the corner points, for example, of the max is a convex programming problem. And so you can come up with relatively simple algorithms to optimize, you know, these corner points for the Mac, and that's how you can. And since you know there's this duality relation, you can trace out the boundary of the broadcast channel capacity region. And not only that, the covariance matrices you get for the corner points, you can convert to the corresponding covariance matrices for the broadcast channel. So it lets you target certain rate points and then do a Mac optimization and then convert those via some equations to the broadcast channel covariance matrices that you need. Okay, so that's the point of this duality. That's why it's useful. Now, of course, there might be other ways of directly finding the right covariance matrices for the broadcast channel rather than going through the Mac. Because you can kind of see there's a sort of a hidden convexity after all because you're doing it via the Mac. So maybe there's a way we don't need to use duality at all. We just do it directly for the broadcast channel. And I'm guessing that should be possible. Now, I don't know if that's been done in a way that I'm describing now, but I think that's an interesting question too. There were a bunch of papers on this. So the most important papers were by the Stanford group, you know, Jindal, and it was basically in Andrea Goldsmith's group. So also Sriram Vishwanath. I guess since he's Indian, I should add his name. Also like Nihar, Jindal, and there was one student who's I'm not sure, with R, but anyways, it was Andrea Goldsmith's group. And in the original paper, I think Stephen Boyd was still on it too. But there were some papers, so this was around 2003 to 5, and there were some follow-up papers around 07 or 08, and there were even some more recent ones that simplified the algorithms. But there weren't a lot of papers on it, I think. It was sort of a certain group of papers. And they go all, as far as I know, they all go through the duality, but I wouldn't be surprised if you can do it more directly. Okay, so these are interesting things to think about, I think. Yesterday we talked about another situation which shows up a lot, especially in wireless, and by the way, also in DSL networks, because you have more than one central office. And cables, copper cables tend to be bundled across, might be bundled, usually within a central office, but usually they're bundled across different boards, right? So you have different separate boards controlling different cables, and so those boards might interfere with each other. That's exactly the same idea as having another base station here with 3 users. Right, these guys start interfering with each other, and so the simplest case is, of course, if we just have, you know, one receiver. So here I just drew the downlink, but it's the same thing for the uplink. So the simplest case to study is the 2 by 2 interference channel. More generally, we're actually interested in, you know, cases like this, right? Because there's interference amongst cells, right? But anyway, it's starting with this case is the simplest case. The interference channel is going to be a 2 input, 2 output channel. We try to study the general model like Shannon taught us to do, namely conditional probability distributions. Perhaps we can do something with that. And then we have 2 separate messages, W1 and W2. And we'll continue this today, of course. Right, and the problem is to send at the maximum. There's 2 rates now, so we have a region, again a capacity region we're interested in. And we focused primarily on the Gaussian case, so the additive white Gaussian noise channel. And we brought this channel into something called standard form, where we here have a unit gain on the first channel plus, you know, I wrote it as a positive number. I guess we could just write it as a general number 2 just to be safe. Because I'm not even sure now if I ever looked at that closely. I mean, usually one is just interested in certain scenarios, but let me leave it open here, that this could be positive or negative. But the important point is here the gains have been made unit, and these gains are zero mean unit variance random variables, which simplifies our problem a lot. Yesterday I wrote this b as root of a1, right? And so I assumed this was a positive number. So maybe I should have written plus minus, but in the end it becomes, you know, all the bounds we had were based, well, except for the converse there could be a negative playing a role, but generally the bounds we had were based on power received. Okay, so we developed a cut set bound, and then what's more interesting, we looked at various coding methods. The first coding method we looked at was treating interference as noise, right? And you can describe that generally for any broadcast channel. It doesn't have to be Gaussian, in the sense that R1 is then just going to be I of x1, y1, and R2 is equal to I of x2, y2, and then we can still optimize over the distributions of x1 and x2. Right, so because we don't know the other users and values, or we don't even try to estimate it, those are the rates we get. We talked about TDM, FDM, so that R1 is some tau. If I write it as a neutral information, it'll be tau times I x1, y2, given x2 is some value like 0. But it could be, you would optimize that value for general broadcast channels, and R2 is tau bar I of x2 y2 given x2 equals x1 equals 0. And for the Gaussian case, of course, we can boost the power by a factor of tau and boost the power by a factor of tau bar in the second time slot, and then we can optimize over the taus. The third strategy was the decoding the interference. So suppose both users decode the interference. If both users decode receivers, decode both, W1, W2, then we have a compound MAC as our model. For which the capacity region is just the intersection, the capacity region of compound MAC is just the intersection of the two capacity regions. So if we had two Gaussian MACs, one with a capacity region that looked like that, and another which has a capacity region which looks like this, then the capacity region of both is the intersection of the regions, namely this, this, and this, as long as, of course, the input distributions for both MACs is the same, namely Gaussian, right? Of course, if this was vector channels, then it won't look so simple. You'd have to take the union of all possible input distributions of the intersections of all MACs, right? That's what you'd have to do then. But for a Gaussian case, a scalar case, it just becomes an intersection. And so we wrote out the region for that. And then what we did is we said, well, intuitively, this works well with low interference, right? Good for low interference. This thing here is good for large interference, as we will see. It turns out this is even capacity achieving. So this is really the one case where the interference channel does permit solution. And this seems to be good for moderate interference. So, and moderate interference is usually the one we have. We usually either have that, or we try to design a system that has either low interference or moderate. It turns out we'd be happy if we had a system with high interference, because then you can get rid of the interference completely. But usually we don't like going there, right? We don't like to build a system with large interference. But actually it's not bad from an interference channel perspective. Of course it's bad for many other things, obviously. So usually we work only with these two methods, so good for moderate. Which might disappoint a little bit, because after all, these are the two methods that we use anyway, right? TDM and treating interference as noise. But okay, but often part of what information theory is involved in is to try to see if there are new methods, and sometimes there are, and sometimes you find that the methods we have are already, pretty good. That's what happens a lot with wireless. People found pre-coding with an inverse filter or linear pre-coding is actually pretty good for a lot of situations. And it doesn't mean it'll be good for all situations, but it's good for a lot of situations. So what I wanted to show you is the plots. Now let's see if this works. So I just wanted to show you the plots. You have these in the, so what the plots show, the resolution isn't so fantastic, but okay. What the plots show is, so this is an example where both crosstalk coefficients are the same. I kind of sketched these ideas yesterday, but here are the computations. So this is rate 1, this is rate 2, so this is the capacity region, this is the cut set bound, this black dash curve. So this is for low interference. Now for low interference, if the interference was 0, of course we would get right to the corner point, right? It's just half log 1 plus SNR, but you see already the cut set bound is knocking off a little bit. This is 10 dB down, interference that's 10 dB down. This is treating interference as noise. It's pretty good. It's probably just the time, I think it is just a time sharing point between that point and that, so we can basically just operate here. If we use TDM FDM, we get the blue curve. As I mentioned yesterday, the blue curve remains the same across all cases because the TDM FDM doesn't even consider the interference value, right? And the green curve shows what you do when you decode interference. So that's the compound MAC, actually with two bounds thrown away that we discussed yesterday. But in any case, oops, I'm sorry. D is decoding interference. Of course, it should be very small because this is a pretty bad value. The green curve. Now I have to try to remember what the green curve is. What was the green curve? The green curve. No, it's true. So both the green and the black are decoding the interference. Both the green and the black. So what is the difference between the two? This one here, you remember I had the compound MAC, and in one case I could throw out one of the error event bounds and like ignore it because I don't care if I get the one right but the other wrong. That's the difference between the black and the green. Okay, so it's a huge difference. Now, most decoders, like if you think of an LDPC code decoder, the green curve will correspond to the case where you are getting rid of the joint error events, namely where both messages are wrong, but you're not getting rid of the error events where the message you're interested in is right, but the message you're not interested in is wrong. How do you build a receiver like that? Right? That's a little bit weird, right? I don't know how to build that. but that's what the theory tells you because we can drop those error events. We don't care about them. So there is a typical sequence decoder that accomplishes this, namely the one that ignores those events. So we're just interested in getting the one message correct. It's just a very big difference. So, I mean, most decoders you build, when you try to decode both messages, you decode both messages, and if you can't decode one of them, it doesn't work, right? So this one here, it says, well, okay, it seems to be possible to make that work. Anyway, that's the difference between the black and the green. Now, suppose we increase the interference level. So now we're at 0.3 in terms of power, rather than 10 dB down, or something else. Now the TDM is best, and here's the cut set bound. Okay. Now I should say there's better bounds than the cut set bound. So probably in this case, it could even be that this point is the sum rate capacity. It might be a little bit off, but it might already be for low interference values. At some point, this point touches an outer bound, and that way we show that treating interference as noise can even be sum rate optimal. Here, TDM, FDM gets better, so the treating interference as noise shrinks, of course, right, because the interference is getting stronger, whereas decoding interference starts moving up, right, so it starts getting better. Both the black and the green curves start getting better, which makes sense because the interference is getting stronger. Then as we keep increasing, so now we're only 3 dB down, that trend continues, and in fact, at some point, these two black and the green meet. So now, at this point, it doesn't help anymore to do what I just talked about, namely the main dominating error event here now is the joint error event, the event where both messages are wrong. Whereas down here, the dominating case was not that. It was where one of the messages was wrong, the other one was not. So it's interesting to think about these things. Of course, this green curve is not one you would want to use in this case. Here you just want to treat interference as noise. Same thing here, you'd want to use TDM, FDM. So up to now there's no point in using anything than the first two. Where it starts getting interesting, so now we're increasing the interference to 1.1, so it's strong interference. It's stronger than the direct link. Now we see treating interference noise is terrible, of course, because the interference is really strong. TDM, FDM doesn't budge, but now decoding interference does better. Okay, in fact, in this case, we'll show in just a moment that this green curve is optimal. The green region is the capacity region for that problem. One of the few cases where the capacity region is known. In fact, there's only two cases where we can, maybe three main kinds of capacity results known. One is the green ones. For strong interference, we have the entire capacity region. For low interference, we sometimes know that point is optimal, and we do know sometimes that the corner points are optimal. So these points here, for some cases, we know that. But that's it. Otherwise, the capacity region of this problem is still open. So especially for intermediate interference, the ones we're usually interested in most problems, like this, or this, not even the sum rate capacity is known. Never mind the capacity region. Okay, so that's an interesting problem. So what we're going to do next is we'll talk about two things still for interference channels. One is going to be proving that we get capacity for strong interference. That won't be too hard to show. And the second thing we'll do is we'll develop the most popular known rate region, the so-called Han-Kobayashi region, which effectively just combines these methods and adds rate splitting. Okay, it combines these three tools with rate splitting. And then I'll say maybe a few words about potential other approaches that were published recently, but we don't know whether they really help or not. So for this Han-Kobayashi region, what's going to be interesting, I don't want to turn it on again in a moment, so let me just show you. Well, maybe I can do it after the break, but what I want to show you after all this, there's the curve I'm looking for, is this. It'll look something like this, the Han-Kobayashi region. Now, in this example, you'll see I've chosen a very high very high powers. So this is like 30. The noise power is 1, so this is like 36 dB, right? It's very high SNR. And the crosstalk is very small. Now when that happens, when the transmit power is large and the crosstalk is small, then something funny happens. The Han-Kobayashi region isn't just a pentagon anymore, like we're accustomed to, but actually has curves that have form like this. 2R1 plus R2 is less than something, and R plus 2R. R1 plus 2R2 is something, which is somewhat unusual, right? So this is the first time we get other kinds of bounds appearing. Again, these bounds only start appearing in certain regimes, namely very high power, very low interference. Then we get, we knock off stuff off the pentagon. So I'll just describe to you where those bounds come from. I'll do that relatively quickly because the derivation, as you here saw when I flipped through all the pages, involves quite a lot of inequalities and simplifying and using Fourier-Motzkin elimination. So if I start at the beginning, we get a lot of rate bounds. We get 7 bounds per user. We're getting 14 bounds. I don't want to write those all out, obviously. Then you have to do Fourier-Motzkin elimination to reduce those. That's what's happening here. And then finally we wind up with one rate region of which we can knock off some more rates. And we wind up with a region that looks like this, which I also don't want to write out completely because it takes a lot of time to write this out. You get a lot of bounds. And the reason you'll see why is because we have a lot of messages. Every one of those messages will be split into 2, and then so we'll have 4 messages, and of course 2 to the power of 4 minus 1 is you're getting a large number of rate bounds. Okay, so that's the program for the next, I don't know, 20 minutes or so. At least for the strong interference. I'll start with the strong interference first to see. So let's talk about strong interference. And the basic idea is the following. Well, let's suppose, first of all, that only one of the values here, one of the crosstalk coefficients is this one here. Suppose A12 is bigger than 1. So I claim if if this crosstalk coefficient has an amplitude bigger than 1, I claim that I can then decode the other user's message. So I automatically get a MAC. And once I get a MAC, I can apply the MAC outer bounds. That's the idea. So let's see what happens. So let's look at this channel x1 plus B. I'll keep it with B12 because it should work also for negative cases. Okay. Now, if I'm inside the capacity region of this channel, just hypothetically speaking, let's say we're inside the capacity region. Well, if I'm inside the capacity region, then I can recover this, right? I can decode the message reliably of user 1, so I can recover this. And if I can recover this, well, then I can just form this, y1n minus x1n, and divide here by b12. And then I will get x2n plus z1n by b12, right? Moreover, I can add a function of x back in, namely b21 x1n. And look at this. This is exactly the signal at receiver 2 except with less noise, because this number here has a magnitude bigger than 1, right? So this signal is less noisy. So anything I can do now, it's actually a degraded version of it, stochastically degraded, but effectively if I can decode, what this means is if I can decode x2 from this, then I can decode it also at receiver 1. So I can decode both messages, right? So this is a less noisy version of y2n. So we can decode W2 also. Okay, so that's the argument. So just by saying that that link is bigger than 1, this guy can decode both. So that actually gives us new outer bounds. Now, if also this coefficient magnitude is bigger than 1, the receiver 2 can do the same, and we get the whole capacity region being the capacity region of a compound Mach, right? And that's the whole argument. So if A21 is greater than 1 as well, then we have a compound Mach whose capacity region is known. Now, we didn't discuss this, but whose capacity region is known to involve decoding both. Well, you have is known. Well, you have to decode both messages. Okay, so that's the proof that the decoding interference as noise as soon as A12 and A21 are bigger than 1, then we have the capacity region. Now, let me tell you the difference. This is called strong. So the very strong interference case that Carlisle studied in an early paper. So if we talk just as a point, very strong interference. The idea here is that for very strong interference, like for the compound Mach I showed, you get a for strong interference you're getting an intersection of two Mach regions. But if the interference it turns out if the interference gets stronger even, then it turns out that the intersection will turn out to become a rectangle. So let's see here. Is there an example? Yeah. So suppose that the interference gets stronger, so the gains get larger. So I guess everything is moving out. So I'd have to think of exactly how that happens. But effectively what happens, let's see here. So if they're both symmetric, they will look like this, and then you'll have this, and I guess then the capacity region is this. I have to think now at what point it's at some point where this intersection just becomes a rectangle. That's the very strong interference case. So what happens is, maybe we can let me write out the numbers first, and then we can see what happens. That's the case where A12 is bigger than or equal to P1 plus 1, and A21 is bigger than or equal to P2 plus 1. So that's the strong interference case. And let's see here. So the intersection. So here, maybe I can write out the capacity region. So for the strong interference case, the capacity region looks as follows. For the Gaussian case. So the capacity region is equal to the set of R1, R2, such that 0 less than or equal to R1 less than or equal to 1/2 log of 1 plus P1, of course. 0 less than or equal to R2 less than or equal to 1/2 log of 1 plus P2. And then due to the interference, we're getting a minimum. So there's two bounds, which causes the intersection, 1/2 log of 1 plus the minimum of P1 plus A12 P2 and P2 plus A21 P1. Okay, so that's the lower, it's the lower piece of the diagonal piece. And what happens is, right, so if these numbers are large, the diagonal pieces just start going out. So if I drew that, so these always stay the same. One of them will have this shape, one of them will have this shape. These two are always at the same place, right? And one of them will have maybe this shape. So it's just that one is stronger than the other. And what's happening is as we increase the interference, the A values, those things are just moving out. So at some point they both just become a rectangle. That's all it becomes. And it's easy to check that happens. If we take the sum rate here, what has to happen is the sum of these two has to become less than that. So what we effectively has to happen is 1 plus P1 times 1 plus P2 has to start becoming less than or equal to this minimum. And P1 plus P2 plus A21. And you can check that should hopefully happen when this happens, right? So if this number is bigger than P1 plus 1, then here we'll get 1 plus P1 plus P2 plus P1 P2, right? So if this number happens, this number gets bigger, 1 plus this gets bigger than that. And same thing, if the other thing happens, then this 1 plus this gets bigger than that, right? So we get a rectangle. And that's what Carlisle studied. So he studied that first, then a couple of years later, maybe very quickly, maybe a year or two later, this was discovered, that a simpler argument that you can extend the result. Okay? That's the very strong interference case. Again, the only general case where the cold capacity region is known for the Gaussian interference channel. So this brings me now to the Han-Kobayashi region. Okay, so the idea of the Han-Kobayashi region is to combine many things together and add rate splitting. In fact, Carlisle already had something similar. Carlisle already did this. So in another paper of Carlisle's in the 70s, probably as part of his PhD thesis, he developed a region which was almost the same as the Han-Kobayashi region, but what Han-Kobayashi did is they added joint decoding. What Carlisle did is he did step-by-step decoding, and they added joint decoding, that you decode all messages that you're interested in at once. And it's likely that that's better. Now, I'm not sure if that's ever been proved. However, usually this name has stuck. Okay? You could almost as well call it the Han-Kobayashi-Carlisle region, but somehow this name is stuck. At least the fundamental ideas behind the rate splitting are already all in Carlisle's paper. What they added was a better decoder, effectively. Okay, so the idea is use superposition coding. And rate splitting. And the reason for this rate splitting is to permit partial decoding of interference. To permit partial decoding of interference. Again, this coding idea really is already due to Carlisle. So I could also plus Carlisle, just to give him the credit for the method, plus to permit partial coding of interference. Okay, so the basic idea is the following. We take this message and that message and we split them. So we take W1 and split it into W1 primed and W1 double primed. This has rate R1 primed. This has rate R1 double primed. And we do the same rate splitting for message 2. W2 primed, W2 double primed, of rate R1 2 double primed, of rate R2 double primed. Okay, so effectively we've converted the interference channel with 2 users and 2 receivers to 4 users and 2 receivers. And the idea of doing this is that one message of each of the splits is decoded by both users. Right, and the other one's only decoded by the direct user. That's the idea. So, decoder 1, so these are the encoders. The decoders, decoder 1 estimates, tries to estimate or decode the following messages: W1 primed, of course, and W1 double primed, those it has to decode, and W2 primed. Okay, so that's the partial decoding of the interference. So decoding part of the message will be helpful because you're going to get rid of some of the interference. Tries to estimate, same thing, W2, W2, double prime, prime, and W1 prime. Okay, so, and the way we're going to do the coding is by superposition coding here and superposition coding here. So we'll have 2 auxiliary random variables. One describing the code book for the common to be decoded message, and then on top of that we'll stack the X1 code book. And similarly here we'll have 1 auxiliary random variable code book and stack. So effectively what we're going to have is 2 LDPC codes here, or whatever, 2 polar codes here, 2 polar codes here, which we superpose on top of each other. That's it. So we'll have 4 codes in the system running. And receiver 1 just tries to decode jointly, like in a Mac, where we could go for corner points. I mean, it's interesting to think about how you actually do this, go for corner points and so on. Now, but I should emphasize again, for the scalar Gaussian channel, doing this kind of stuff makes sense only for very high power and very low interference. It doesn't make sense anywhere else. Now that doesn't mean for other channels like vector channels, there this certainly will make sense, I think. Because for vector channels, for example, think of OFDM. Some of the subbands might have strong interference, and some of the subbands might have moderate interference, and some of the subbands might have weak interference, right? And if one of the subbands has strong interference, we should decode the interference from that subband. But the interference of that subband will be represented exactly by this, right? It's just the, the code operating in that subband, and the message, the sub-message operating in the subband then corresponds to this, what you're decoding, okay? So for the scalar Gaussian case, though, this method really, I don't think I would ever use this. It's a big mess, and you're getting very, very little gain out of it, unless you're in really exotic regimes, Okay, so coding, maybe I can quickly just write that, then we'll write out maybe, so the coding goes like this, and so that at encoder 1, this is our code book. I'll just draw it like this. We choose 2 to the NR primed W1 primed, right? So there's going to be, we random code this using a distribution PU1. So, well, choose PU1X1, PU2X2. Of course, X1 and X2 have to be independent, at least conditioned on a time-sharing random variable. So everything we do later, we can add a time-sharing random variable, but let's not do that for now. So we generate a code book like this, where we have 2 to the NR W1 primed runs from 1 to 2 to the NR 1 primed. Then on top of that, we stack another code book. I'll just write it like this: XN W1 primed W1 double primed. Here we're going to use the distribution PX1 given U1. So for every letter, we have more code books, but for every code word here, we look at every letter and conditionally generate a letter here, second letter, conditionally generate a second letter, and so on. And we do that, of course, for W1 double primed for 1, 2 to the NR 1 double primed. And then to transmit, we just take these 2 messages and send the X, and that's it. And the user 2 does the same thing. You could design this like described. We take W1, split. Here have your first encoder, encoder 1 primed. Here we'll have a second encoder, for instance a polar code or an LDPC code, literally, right? You could just take those bits and stuff them into a code. And then here we'll get our V1N, and here we'll get a U1N, and then we'll just, you know, scale those properly, but anyway, we just add them up. And that's our X1N. So that's the practical way of doing it. And that's how Carlisle described it, is exactly like this. Okay, now what Carlisle did, just to emphasize, he did sort of step-by-step decoding. He first decoded one, he did successive interference cancellation. That's what he did. Whereas Han Kobayashi did, oh, we'll do a joint decoding, and it could be that the joint decoding sometimes is better. I don't know if there's an example to actually prove that. It could be that step-by-step decoding is just as good. And I'm quite sure that there's tricks to make it just as good. But anyway, still the Han Kobayashi regions is nicer. It's a more uniform description. So anyway, this is then again mimicked here too for user 2. Okay, so let's stop there since it's already 20 after. Then after the break, I'll talk about the decoders, but they're just going to do joint typicality tests, as you'll see. And then we'll write out the regions, at least we'll sketch the main parts of the regions, and then I'll say a few final words. I think that's all I really wanted to say about the interference channel. There would be a lot more to say about the interference channel, but like interference alignment and vector channels and all this stuff, and but I don't have time to do that also.
Can you give intuition why you required rate splitting here?
Because sometimes, here's an example. Suppose we have an OFDM, suppose we have 3 subbands we're communicating with, right? So we're just using the frequency diversity, right? So here's a channel with a bandwidth. We split the bandwidth into 1,000 subbands by using OFDM. Some subbands might have strong interference, some have weak interference, some have moderate.
So depending on what kind of thing your strategy...
Absolutely. So in those subbands with strong interference, we should decode the noise. That's why we need... So what this rate splitting does, it's an abstract way of including all possible ways of doing this, even in subbands. Do you see what I mean? Like, you wouldn't actually do it the way I'm describing here. You wouldn't add it up.
Rate selection would also depend on what kind of interference in some sense.
Yes, oh yes. The amount that you're splitting will depend on. So for instance, for the subband example, if 1/3 of the subbands are strong interference, you'd probably choose 1/3 to be decoded at both and 2/3 not, right? So and that's reflected also here. I mean, here what I could do is just now multiply by e to the j 2 pi f, 1t and e to the j. I mean, I'm writing it as time, but you get the idea, right, of I over time, it's a vector, and e to the j 2 pi, right? And then I would be modulating this onto one subband and modulating this on, like all those kinds of ideas are included by this superposition coding. That's why, like, a lot of these information theoretic tricks, they look simple, I think, when I'm describing them, but they can become really sophisticated coding methods. They're all included in these kinds of structures because we have arbitrary probability distributions. These letters could be huge. They could be vectors across all subbands, you see. And then they represent very general possibilities. It's the typical thing that even though the information theory looks so simple and so limited, once you realize what it means, it's actually extremely general. And the optimizations should then be done, can in principle be done on that complex object that you're working with. Like many subbands, I think is the easiest example. We could talk about vector channels and singular value decompositions. That's the same thing as subbands, right? Or whatever, you want to, whatever you like. Right. Okay. So it's interesting. When you schedule, if you're designing a comp system, a coordinated multi-point where you have base stations cooperating, you should well, cooperation is different than it's a broadcast channel. But if you can coordinate what you do without sending the data across, like there's different levels of cooperation. But if you could, if you saw that there was strong interference, you might schedule interference into a person that isn't really interested, because if that person is capable of decoding both, you would boost the person's rates. You see what I mean? Rather than treating interference as noise or applying TDM. You might want to deliberately hit someone with interference, depending on what the spectral profiles of both receivers are. Now this idea, I talked to just people I met at conferences already back in 2008 or 9 or 10. I met some engineer, again from Qualcomm. I guess they like to talk about these things. They were doing that already, or they were thinking about that. They had this idea that maybe we should send in cases where the interference is strong, we'll use our successive interference cancellation technology for cases like that. And the idea then is to schedule into those subbands, right? And that's what the theory tells you to do too, because you'll boost the rates in those subbands. Of course, it needs very smart infrastructure to do that, and also mobile devices potentially. Although the other way, the base stations would only have to get smarter. The mobile stations would only have to schedule, right? Because both directions are interference channels, both ways, up and down. Okay. Any other questions for now? I mean, those things, yeah.
Why, in case of rate splitting, maybe successive interference cancellation cannot be joint decoding? Is it because of rate splitting?
No, it can always be joint decoding, but successive interference cancellation is often simpler, right? Because, for example, you don't have to decode both at the same time. You're only decoding one at a time, so it's natural to think about. But as we saw, there might be other ways of doing it, joint decoding, like with time shifting or with soft message passing and so on. So there are various variations. Like successive interference cancellation can be done in many ways. One is via turbo processing. Then it isn't really soft interference cancellation anymore. It's actually a turbo processing loop, right? It's where you pass log likelihood ratios back and around. And that, of course, that can start getting better rates. And then you don't have to do time sharing, which is what you would have to do with successive interference cancellation. But here, of course, you're just being opportunistic. If there's no time sharing necessary, right? If you can decode the interference, you do, right? But there's all sorts of problems. Again, then you'd have to have a code that works only in that subband, right? You can't code across the subbands anymore, right? That's again a restriction if you're decoding. So there's a lot of things you'd have to think about when you actually implement something like this. So, but still, in principle, that's what you should be doing. Okay, I think most people are probably happy to go to the break, right?